All right, so in this video, we are going to be continuing our derivation of the C6h character table. And where we got last time was we figured out how the z and the z vector, or the z function, transforms as this gamma 2, and that x and y transform together as gamma 3. And so at this point, what we just have to do is continue to test functions to try to derive more irreducible representations. We know that we have a total dimensionality right now across these three vectors, gamma 1 through 3, of 4, right? 1 plus 1 plus 2. But we have a 12-dimensional space. So eventually these numbers are going to have to sum up to equal to 12. Once we get to that space, once we get to 12 and we know that we have valid vectors, they follow the orthogonality rules and all these other character table rules, then we know we'll be done. So let's try to do gamma 4. And what we're going to do here is a little bit of a trick, which is that we can see that, we want to test quadratics. And there's the quadratics of the d orbital functions are xz, yz, x squared minus y squared, and xy, and also z squared. And what we can do is use the fact that we see that the z function has some negative ones, and the xy function transforms as this irreducible representation with gamma 2. And what we can do is then figure out what would happen to xz. The function xz is going to transform together with yz. And well, xz is just x times z, and yz is just y times z. So you know that they're going to transform together because xy transforms together. And it's going to be very simple to figure this out. You're just going to have to multiply these components. And in other videos for other character table derivations, I've explicitly shown how this transforms. It's quite simple, but basically you're going to walk through each operation, and because z goes to negative, in the cases where z goes to negative z, you're just going to get the negative of the answer of what you got for x and y. So the end result is that you can just multiply these two irreducible representations, and that's going to get you a unique a gamma. So that's quite nice. We can go a little bit further though, right, and do something what ends up being a little bit harder, and that's going to be the function xy, right? The function xy, now what do, right? And what we actually have to do is, it's not just a simple multiplication issue. We can't just do x comma y squared. That doesn't really make sense. And so what we have to do is we have to see how this transforms. And so we'd start off with the identity. xy goes to xy, of course, with the identity taking everything itself. And then we get to C6, and we ask the question, how does xy transform? We have to recall our rotation matrix, 2 by 2 rotation matrix, which was cosine 2 pi over 6, which is also pi over 3, negative sine pi over 3, and sine pi over 3, and cosine pi over 3. So this tells you that x goes to cosine pi over 3 minus sine pi over 3. X transforms when the C6 operation is done on it, transforms as cosine pi over 3x minus sine pi over 3y. And so that's what x does. And then what does y do? Y goes, following this matrix, bottom part, sine pi over 3x plus cosine pi over 3 y. And so we can multiply this out, and I'm keeping it generic at this point so that then we can see a relationship that can be extended to these other operations. If we evaluate this and say, cosine pi over 3 equals 1/2, etc., we're not going to be able to see those relationships as easily. So now we FOIL this out, and we end up getting cosine pi over 3 sine pi over 3 x squared. Then we can do the minus terms, minus cosine, or the y squared terms, the y terms, cosine pi over 3 times sine pi over 3 y squared. And then we have a minus sine squared pi over 3 xy plus cosine squared pi over 3 xy. And so we may be able to see is we can factor out an xy here, and we're going to be able to factor that out as cosine squared pi over 3 minus sine squared pi over 3. And there's a trigonometric identity to utilize here, which is that cosine squared of x minus sine squared of x turns out to equal cosine 2x. So this is just one of these trigonometric identities. And so really this is going to change into cosine 2x, right? Cosine 2 pi over 3. So cosine 2 pi over 3 xy. And this part we can factor out cosine pi over 3 sine pi over 3 x squared minus y squared. What's interesting about this is now we can see how xy transforms as a linear combination of xy function, but also x squared minus y squared. And that's a d orbital function. And so what's telling us is that x squared minus y squared and xy transform together, just like xy did and xz, yz. And so now what that tells us we have to do is we have to ask the question, how does x squared minus y squared transform? And up here we know for identity, x squared minus y squared just goes to x squared minus y squared. So we're going to have a 2x2 matrix that explains that mathematically signifies that transformation. That's the identity matrix. That equals xy, x squared minus y squared. And then we can take the trace across this matrix that has ones across the diagonal. And that's going to get you the chi, the character of the identity, equals just the sum across that, which is 1 plus 1 equals 2. And so our gamma 5 here is going to have a value of 2. But anyway, now we can go back to C6. We figured out how xy transformed. Now we have to look at how x squared minus y squared transformed and get it into a linear combination, again, of xy and x squared minus y squared, since we figured out that those two functions transform together with this gamma 5 symmetry that we're determining. Gamma 5 irreducible representation, I should say. So we have x. We know x goes as this term. So it's this term squared. So let's FOIL that out. It's going to get me cosine pi over 3 x squared plus sine squared pi over 3 y squared minus 2, right? We have two of the same terms here. Cosine pi over 3 sine pi over 3 xy. And then we have to minus the y squared term. So we're going to take this and square it. We have to remember that we're going to have negative signs there. So it's going to get us negative sine pi over 3 x squared minus, remembering that there's a minus sign on all these, minus y squared cosine, sorry, this should be squared, cosine squared. I got to make that nicer so we don't think it's a 2 pi over 3. Cosine squared pi over 3 y squared minus 2 cosine pi over 3 sine pi over 3 xy. And so now we can see we have some relationships here. Cosine squared pi over 3 x squared minus sine squared pi over 3 x squared. That is this same sort of trigonometric identity where it comes out to cosine 2x. So that's going to simplify as cosine 2 pi over 3 x squared. And then we have this y squared term, which is sine squared pi over 3 y squared minus cosine squared pi over 3 y squared. Well, that's the negative of this term, right? If we minus this out, we got a positive sign of minus cosine. So that's going to become a negative cosine 2x, or 2 cosine 2 pi over 3 y squared. And then we have this these two terms here that go as 4 cosine pi over 3 sine pi over 3 xy. And so we can now factor out a cosine 2 pi over 3 and get it in terms of x squared minus y squared. And this other component is already in terms of xy. So again, what's so beautiful about this is that we have shown that x squared minus y squared transforms as a linear combination, some constant times x squared minus y squared and xy, just as xy did, right? We had something times xy and something times x squared minus y squared. So then we can write the matrix for this transformation, right? It takes xy and x squared minus y squared. And really, just to save us time on writing, we only care about the on-diagonal elements, right? And what are those on-diagonal elements? Those are the elements that in which, like for example, for xy, it's the constant that is multiplied by xy. This would be the off-diagonal element, the constant that's multiplied by the other term. So the on-diagonal element there is cosine 2 pi over 3. And similarly, for x squared minus y squared, the on-diagonal element is, there's x squared minus y squared, the constant, cosine, same thing, cosine 2 pi over 3. And so our trace of our matrix, chi of C6, is going to be equal to cosine 2 pi over 3 plus cosine 2 pi over 3, right? Which is 2 cosine 2 pi over 3. And 2 pi over 3 is 120 degrees, and so that cosine is -1/2. So we're going to get a value of -1 here. So different from what we got for gamma 3 and gamma 4. We can generalize this equation. What's nice is we can think about this for any C6n, and it's just going to be 2 cosine 2 theta, where theta is how much we rotated by. In this case, we had C6, so we rotated by 2 pi over 6, which is pi over 3. That's why we had all these pi over 3s here. But then we had this relationship, this trig identity, which we took advantage of, which turned cosine pi over 3 into cosine 2 pi over 3s in this final matrix, which gave us here. So now that gives us a generic answer of 2 cosine 2 theta, where in this case theta was equal to pi over 3. What about for C3? That's our next character. Now very quickly we can come up with these answers, right? For C3, theta equals, so this is C3, theta equals 2 pi over 3. So our chi for C3 is just equal to 2 times cosine 2 of that, which is 4 pi over 3. Cosine 4 pi over 3 is 240 degrees. That still is -1/2. And so that is -1/2 times 2 gets us -1. So this was -1 as well, just for clarity there. Okay, what about for C2? We can actually do the same thing if we want. For C2, we're rotating by pi, right? We're rotating by 180 degrees. So our chi of C2 is actually equal to 2 cosine 2 theta. theta is pi, so 2 cosine 2 pi. Cosine of 2 pi is 1, so this gets you 2. And if you think about this, another way you can think about this is that for a C2, let me just, I'll write it in a different color, maybe just up here. For a C2, this is just our alternate way of thinking about it. C2 takes x and goes to minus x because it's spinning an x vector 180 degrees. Right? Remember, we got our x, our y, and our z, and this is our principal rotation axis. So if we're doing an x vector, we're spinning that all the way around to negative x. And similarly, y would spin all the way around to negative y, and so xy would go to negative x times negative y, which equals xy. So xy just went to itself. And then if you think about x squared minus y squared, well, that would go as the quantity negative x squared minus the quantity negative y squared, because x went to negative x and y went to negative y, and that just equals what you got back. And so you would end up with this matrix, this 2 by 2 matrix, where we're asking what happens to xy and x squared minus y squared. We know they transform together. And you get the identity matrix because they both went to themselves. You take the trace of that matrix, and lo and behold, you get the same thing as our generic formula, which is 1 plus 1, which equals 2. So pretty cool how that all works out and checks out. But let's keep going on here. Now, if we do C3(2), that's a 4 pi over 3 type of theta. And so our chi of C3(2) is equal to 2 cosine 8 pi over theta, 8 pi over 3, excuse me. And so 6 pi over 3 is a complete rotation, revolution around, 360-degree rotation, because that's 2 pi. So this is the same as 2 cosine 2 pi over 3. And 2 cosine 2 pi over 3, we know was negative 1. So this is just negative 1. So again, we go here and we write a negative 1. And then we keep marching along here. If we have a theta of 5 pi over 3, well, that is what a C6h does. And so that's going to be 2 cosine. Now, again, remember the generic formula is 2 cosine 2 theta, 2 cosine 10 pi over 3. Well, 2 cosine 10 pi over 3 is the same as cosine 4 pi over 3, because 6 pi over 3 is a 2 pi complete rotation. So that again, 2 cosine 4 pi over 3 equals negative 1. And so again, we get a negative 1 here. For inversion, it's going to be very similar as this green text here. In fact, the exact same. So I'm not going to write it all out, but I'll just remind you the definition of inversion is that any generic point x comma y comma z goes to negative x, negative y, negative z. And so x is going to go to negative x, y is going to go to negative y, and xy therefore is going to go to xy as you times those two negatives out, and x squared minus y squared also goes to itself. And so you're going to get a chi of 2 from this identity matrix here. So that's going to be equals to 2. And then for these improper rotation axes, we can just work through it. So I'll do it over here. We have S3, 5. Let's actually first do sigma h. This will save us some thinking. So let's do sigma h over here. Remember, the sigma h is in the xy plane. It's perpendicular to principal rotation axis. So x and y vectors don't do anything. So x goes to x, they stay the same, and y goes to y. And so this is also going to get you the identity matrix, okay? Because they went to themselves. So that's going to get you 2 here. And so now we can work out for improper rotation axes. We have S3 5 times. We know that's equal to a C3 5 times, followed by sigma H 5 times. But a sigma H 5 times is the same thing as a sigma H because it's an odd number, and a C3 5 times is the same thing as a C3 2 because C3 3 is a 360 rotation, so we only have 2 more rotations after that. So S3 5 times is just like doing a C3 2 followed by sigma H, but we know sigma H does nothing, the XY vectors, but a C3 2 is worth a -1. So the character there is going to be the same as C3 2 is -1. What about S6 5 times? That's equal to a C6 5 times, followed by sigma H 5 times, which is equal to just a sigma H. And we know sigma H for X and Y does nothing. So for XY, it's going to be doing nothing. So we're just going to get the same character as for C6 5, which was -1. S6, our second to last one here, is C6 followed by sigma H. Again, we know sigma H drops out. So we just look for the character in our C6, which was -1. And our very last one here is S3. That's equal to a C3 followed by sigma H. And the sigma H drops out for reasons we talked about before. We looked at the character under the C3, and it's a -1. And so that's how we derived another sort of irreducible representation. We showed that x squared and x squared minus y squared transform together. And all of these should be orthogonal to one another. So you can test this. And when we do the orthogonality, we mean that the dot product has to be equal to 0. And so that's multiplying each component and adding them all up with the 2 different vectors. But for group theory, you have to also normalize by the number of symmetry elements. In this case, the number of symmetry elements in each class is just 1, so you don't have to worry about it. You're going to be multiplying one of the vectors all by 1. So practically what that means is that you just have to test, gamma 5 dotted with gamma 1 should be equal to 0, gamma 2, gamma 3, gamma 4. All the different permutations should be orthogonal. We haven't tested any of those yet, but you can see it should be true. Gamma 5 dotted by gamma 1 is a really easy one to do because you're multiplying everything by 1. So it's going to be 2 times 1 plus 1 times -1 plus 1 times -1. Well, if you're just timesing everything by 1 and then adding them, it's the same thing as just adding all these. And look at that. That's going to get you 2 plus -1 plus -1 plus 2 plus -1 plus -1 plus 2 plus -1 plus -1 plus 2 plus -1 plus -1 equals 0. You can check this for the other ones. They're also going to be equal to 0. So we have a 2 plus 1 plus -1. That gets us to 0. -2. That gets us to 2 plus a -2 gets us to 0. And this cancels out. That's a 0. We're at +2. We're at 0. Now we're back at 0. We're at 0. So it all works out this way. So we're getting closer here. There's one more function that we have to derive. And this function is going to be a cubic function. And you just have to test different functions and look for these patterns. And as you practice deriving these character tables, it'll get easier and easier to actually see these patterns. But from this one, what you can actually get very quickly is if you use a cubic function and multiply xy, the irreducible representation that we just derived, if you multiply that by z, you'll get something unique. And so you can imagine, look at these values. These values for gamma 3 and gamma 4, they're the same. They only differed, these gamma 3 and gamma 4 only differed because this one was the negative of this one because we multiplied by z. Well, here we have something, gamma 5, that looks exactly like gamma 4 on the back end where we could multiply by z and have these -1s. So we could generate a new function very easily, that should tell us, by taking these functions and multiplying by z. And that's exactly what ends up being the easiest way to solve this. So we'll call this gamma 6. And the functions now that we're talking about are cubic functions. So these functions have use because they have the same symmetry as the f orbitals. And so what we're going to find when we multiply this by z is the cubic functions are x, y, z, and z x squared minus zy squared. Of course, you could also write that as z times quantity x squared minus y squared. But these are going to transform together. Now we just have to multiply through. So we're multiplying gamma 2 by gamma 5. So again, the first 6 characters here are all 1s for gamma 2, the z function. So we're just going to copy from gamma 5 above. 2, -1, -1, 2, -1, -1. And then we have -1s for z. So we have to take the negatives of all of these as we multiply by -1. So -2, excuse me, 1, +1, +1, -2, 1, and 1. And at this point, something quite remarkable happens, which is that we realize we're almost done here. And why I say almost is because we're not quite here yet. There's some problems, and I'll get into that in a minute. But why we're almost done is because 1 + 1 + 2 + 2 + 2 + 2 is equal to 10. And so we're getting close. And so the next thing that we have to do is just figure out two more functions or 2 more irreducible representations that get us to a dimensionality of 10. Total dimensionality of 10. Total dimensionality of 12. We're at 10 right now. We need a total dimensionality of 12. Okay. And so the way we're going to do that is we're going to puzzle it out using the orthogonality theorem. Okay, the orthogonality character table rule. Again, look at the character table rule video to learn about these different rules I keep referring to. But that will get us our dimensionality of 12 in total and get us that much closer to deriving this C6H character table.